Right. Okay. Okay, so intersection of planes, we talked a little bit about this already, and we've learned how to use our calculator for systems of equations, which with Cartesian equations of planes, that's what you're actually doing when you're solving those systems. So think about the orientation of three planes. So that's a map that we're going to look at. Okay, we've already talked about two planes. So two planes. Remember, the same plane, infinitely many parallel planes, no solutions. For non-parallel planes, a line of intersection. So if you have two planes, you can never get a point only. Okay? Three planes. The orientation, it's shown there. So those are parallel, so they're all different. So one's on my stool, one's there and there. Okay? You could also have two being parallel and one not. When you're looking for the intersection of all of them, there's nothing, right? So parallel planes will only intersect if they're the exact same plane, right? And that will be infinitely many solutions. You can have then, down there, two parallel. So let's say that one and this one, and then non-parallel. So if I show that like this, that's an orientation, but there's no solution between all three, right? Because, yeah, there's a line of intersection there, but then it keeps on going down to this one, and it intersects that separately, okay? When they three, so that is this, that's on its side. If we have three that where none of them are parallel, that's like a book, right? So three meeting in the spine of your book, right? That's a line of intersection. Okay, so infinitely many, but it's a line. You can have these three all not parallel, but they meet in, we call it a triangular prism. So three separate lines of intersection, not the same. Those three lines turn out to be parallel to each other, but they don't intersect. Okay? And then we talked about that one. This one, that's where they meet all in a point. Okay? So kind of looks like the three-dimensional plane where this is your y, this is your x, and this is your z. So they meet in the center there, like the origin. Okay? So you can have a single point, a single line, or three planes, all the same, infinitely many. Okay? So there's different situations. So that's what we're going to look at today. Okay? So there we go. So there, two planes are defined. Determine the line of intersection. So we've already kind of given you a hint. So we're just doing two planes together. It says determine. It doesn't say algebraically determine. So we may do some algebra work, but you can use your calculator to help you, right? So you could set up your planes here, your system as a matrix. So 1, 2, 3, 6, 2, 3, 1, 7. All right, so matrix edit. This is a 2, 5, 4, and then 1, 2, 3, 6, 2, 3, 1, 7, and then I'm going to ref it, RREF, row reduced echelon form on matrix A. Okay. So 1, 0, negative 7, negative 4, 0, 1, 5, 5. Okay, and so then we kind of looked a little bit at this when we learned about solving systems using the calculator. Because it's 2 equations in 3 unknowns, we're going to let either y or z be a parameter. I would always let z be a parameter because this is already, if you're using RREF, then this is down to a 1. So here, right, because this really means y plus 5z equals 5. So if I let z be, say, parameter t or lambda or whatever you want, then I'm going to have y equals 5 minus 5t. Okay, then back up to the top equation, I'll have x minus 7, actually I can just solve for x right away. So x will equal negative 4 plus 7t. Okay, and then it says line of intersection, so it didn't specify the form of that. So if you were to leave it like that, that's not really great because it's not in order. So you could leave it sort of like this, but rearrange it so it's x, y, and z. What I would prefer is to put it into a vector equation. Okay, so just read the question carefully on that. So your position vector is all the constants. So for x, it's negative 4, y, it's 5, z, it's 0. And then your direction vector is 7, negative 5, and 1. Okay? Now, when you do this, when I did this, I got this. You might do it and maybe let t be something else, like a multiple of t. Or you rearrange them and, I don't know, didn't do RREF, all right? You might have some multiple of that direction vector, which is fine, okay? Or you might have a different point, which is fine as long as it's a point on that line. So there's more than one correct answer for any line that you're giving in vector form, but there's a lot of wrong answers too. So your direction vector has to be at least a multiple of that, okay? I always, even if I got something that was multiple, I often put it in lowest terms per se, but it would be parallel, okay? And then of course, if it's a different point, you got to make sure that, like if you're comparing, say, the answers in the back of your assigned questions, then if you have a different point, then check your point on the equation that they give and make sure it works. And then you know you've got the correct one. Okay? So that's a line of intersection. Now we're doing 3 planes. Show that the planes meet only at a single point by solving the system of equations. You actually are told. Okay? Things to look at before you even, if you weren't told, things to look at are the normals of each plane, right? Because then if they're parallel to each other, then you know, okay, well, it either has infinitely many or none. If you take a look, they're not, so that's 2, 1, negative 1. If you wanted to just look at them, 2, 1, negative 1. 1, negative 2, 3. 3, 5, negative 1. They're not parallel to each other. Again, it doesn't mean that they intersect in a point, but that's one of the possibilities. So you can set up a system here of a matrix. Again, it doesn't say algebraically, so you can use your calculator. All right, so matrix, I'm going to edit on B. This is a 3 by 4, and 2, 1, negative 1, 2, 2, 1, negative 2, 3, 7, 3, 5, negative 1, 0. Okay, put out of that. Matrix math, REF, the matrix B. Okay. So 1, 0, 0, 2, 0, 1, 1, 0, 0, 1. Right, so anytime you get 3 by 3 on the left there, the equal sign, with a diagonal of 1s and 0s everywhere else, okay, you know you're going to have a point of intersection unless this, yeah, that'll be fine. If you had 0s here and a number, then you wouldn't have any points of intersection. But this, as long as you have something like this, then you know what your point is. It's 2, negative 1, 1. Okay, because we're talking about a point, show it in that sense. Yeah.
If this is one is the 3 point, does that mean that the points are perpendicular to each other?
It doesn't have to be perpendicular, but it's kind of like, that's one example where like the origin, but it could be like one could be slanted.
Okay.
It's still one, right? Yeah, not necessarily perpendicular. Okay, if you turn over to question 3, again, it tells you what the orientation of the planes is going to be. So it says, show that the 3 planes defined by those equations form a prism, that triangular prism. So if you try to solve this, that means you're not going to get a point or a line of intersection. Okay, you can take a look at, again, you might want to look at the normals. Not that in this case, for a prism, they're all going to have different orientations, but it's a good idea to get in the practice of this when you get to a test. Okay. So when none of the normals are parallel to each other, that's one of your options, right? Is here or here or here, okay? When none are parallel. So you're given that it's going to be this. We have to show that. So think about it. That means every pair of planes intersects in a line, okay? And then what about that? Well, so if we find the intersection of these 2 planes here, that line, then we find the intersection of this plane and the bottom one per se, that line. Those lines are parallel to each other, but they're not the same. Okay, so they're parallel and distinct from each other. So that's what we want to look at. Whereas here, if we do this one and this one, we get a line. We do this one and this one, we get a line, and they're exactly the same line, right? Because that's the intersection of all three. Okay. All right, so sometimes capital pi is used for describing planes. It's kind of like a capital letter. It's a big pi. So we'll find the intersection of plane 1 and plane 2. So again, 1, -1, 1, 2, 2, 3, -1, 4. For fun, you might want to do one of these algebraically. I think the solutions I have in Schoology are algebraically, just so you can see that. Okay, so this is a 2 by 4. 1, -1, 1, 2, 2, 3. Okay. Okay. And I'm going to go math back. Okay. Okay, so there are fractions in there. That's where I would let my parameter at z not just be t, but whatever the denominator is, so that you get rid of, you don't have fractions to deal with. So this here is y minus 3/5 z equals 0. So I'm going to let z be 5t. Then I don't have to deal with fractions. With a direction vector in a equation of a line, I really don't want fractions for your direction vector because you can just multiply it by scalar. Okay? Your point could have fractions. I'm okay with that, but I don't want fractions in the direction vector because that's a simple multiplication by the common denominator, right? So then y equals 3t. And then x equals 2 minus 2t. I'm going to call this R1 for the first line of intersection. And then do the same for, so we did that for pi 1 and pi 2, plane 1 and plane 2. Now we'll do the same. going to use a different parameter since it's a different line. And r equal negative 2x Okay, so notice how I get the same direction vector. My point has fractions, that's okay, but my direction vector doesn't, and it is the same. So just looking at that, you actually don't know, maybe that is the same line, right, if you weren't given the hint in the question. So if you've started doing this separately without solving the whole system together, maybe look at that. How do you tell if it is the same line? Because this is the same. You can just test, is this point, does it satisfy this equation, or does this point satisfy this? So you would put 2 in for x, 0 in for y, 0 in for z. So if you did that, 0 in for z here, you get mu equals 0, okay, which means this would be gone, right, and those are not equal to each other, right, so you can just by inspection see that they're not the same line. Okay, and then intersection. So we've done first plane and second, second and third, so first and third. Well, I'm gonna use, just because if you are talking about different values, then then you're kind of making, you call them all t's, when t is, if you did substitute t equals 1 in there, then you're getting a different point than if you do t equals 1 here, kind of thing. So, just within the same question, it's better to keep them stuff different. Okay, so again, you can see that, so these are all parallel lines. Okay, so we know they are all parallel. We did check, so check to see if a point from R1 lies on R2. Okay, so we did that visually, checking to see if the lines are parallel or coincident. Okay, and then we can check the same point, 2, 0, 0. So basically, if we have, again, use the zeros, that's kind of easiest. If we put 0 in for y here, we would have lambda equals 0. So that would go to 0. That point isn't the same as that. Okay, so point from R1 does not lie on R2 or R3. Okay, so that checks to see that that first line is not on either of the two other ones. Then you want to check those other two lines to make sure that they're not the same. If they were the same, then it would be two planes intersecting separately, maybe parallel. Yeah, they could be parallel, but we've already checked to see if the planes are parallel. So likely that's not going to be an option, but you kind of want to cover all your bases just in case. So R1 and then point from R2, well, let's check. So this one again, I would choose the 0. Okay, obviously if this was component is 0, it can't be in both of those places. So that's kind of obvious, actually all three, because the Z coordinate is 0 on all of them. So therefore, these planes intersect in a triangular
Checking for different points. Can't you solve a fourth system with the 3 different plane equations and see that there's no solution between those 3? And so you know that they're all separate.
Yeah, true. Yeah, like if you know, let's just see. If you do that, you'll get no points of intersection, right? You do, so that's good, but then to be specific about what kind of orientation.
You do have to do this.
Yeah, for
Okay.
showing that it's a triangular prism. Because remember, there are no solutions in this and this and this. Now these ones have two parallel planes. So I guess if you just compare the normals and say in words, right?
Right.
Because when you try to find the intersection, like if you do the 3 steps that we did, if it was like this and you tried to get the intersection there wouldn't be any. And this, there wouldn't be any either. So
Okay.
there are more than one case where you have no points of intersection of the whole 3, so you have to do some explaining,
Okay.
not just the matrix of the 3 of them. Okay, and then question 4, find the line of intersection between the 3 planes. Again, it's giving you a hint, right? So this one, there is an intersection, right? You're told that it's a line. Even if you weren't told, you could do all 3 of them together, right? So, okay, so we could solve the system here all together. Looking at the normals before we even do that. So if you just look at the normals right away, you know that none of them are parallel to each other. So it's not going to be a case of 2 parallel and 1 not. They're actually going to meet in that sort of spine of the book in 1 line, based on the fact that they're not parallel to each other. It's 3 by 4. 1. Okay, so infinite number of solutions. We're told it's a line. That's confirmed. Okay. So here, it's kind of like when we were doing this intersection of 2 planes. So that'll be y minus 3/5 z equals 0. So I'm going to let z be a multiple of 5. Okay, so let z be 5t. So this is we just basically, if you look back at the actual equations of these planes, we just changed one of them from the last question. Yeah, exactly. Yeah. Okay, so what's another way you could do? So if you know that, if you're told that they intersect in a line, if you found the intersection of two of the planes, okay, found that line, it would be that. And then what you could as well do, if you didn't do all three, for whatever reason, you did two, you could take that line and make sure that it's a line on your third plane, okay? Because if it's a different line, it's not going to be on your third plane. There's not going to be a line of intersection, okay? So it's just another way of thinking about it, okay? Last one, notice how it says describe. You don't actually have to calculate anything. It says describe the intersection. So are there no points, one point, infinitely many, and what is the type of intersection? What's it going to be? A line, a plane, that kind of thing. So you've got your three. I would look at the normals. Some of these, again, we kind of use the same planes, some of them. And you'll notice, okay, that those normals are all parallel to each other. So the planes are parallel, first of all. Okay, so then you have to think about, are they parallel and coincident, two parallel and coincident, one not, or all three different? You actually take a look back here. We multiply this by 2, we get this. So those are exactly the same plane. If we look at this and multiply by 3, we get exactly the same plane. So it's very similar back to Math 10. When you had two Cartesian equations of a line that were just multiples of each other, they are the same plane, right? So in a way, you didn't even have to look at the normals, but it's a good process to always do that. They are parallel. Actually, I'll just review. I'll get back to it. Planes are parallel and coincident. Okay. As point 2 is I'll call this point 1, 2. So, therefore, there are infinitely many solutions. And the solution set would just be choose one of the equations. I'll choose the simplest form equation of the plane.